Hello, today we'll be learning about molecular formulas, specifically naming simple compounds. Naming basic compounds. Note that this is a continuation of my naming ions section. So as we learned before, the metal name remains the same while the non-metal ending gets the "-ide". We have two examples here, Be3N2 and CaCl2. So we start by looking at the individual elemental symbols. Be stands for beryllium, which you wrote down over here. And then we move on to the N, which stands for nitrogen. But we know that when they are alone and not with a different compound, such as NO2 or NO negative in a case, we add the "-ide" ending at the end. So here, N2 becomes called nitride. I'll talk more about how we got these subscripts later in the video. Same thing with calcium chloride here, as I named it calcium chloride. We start with the Ca, which is the elemental symbol, which stands for calcium. So the metal name remains the same, calcium. Then we have chlorine at the end here, by itself essentially, not considering the calcium. So as in, it's not ClO or ClO3, it's not attached with another nonmetal. In this case, Cl2 would become called chloride. So we take chlorine, change the ending, add the "-ide", and we get chloride. Writing basic compounds. We'll start with an example of finding the formula of tin 2 fluoride. We begin by finding the charge of the individual elements. Some of these can be found on the periodic table. However, some others, like transition metals, have to be given to us, such as here we see that we have a tin 2 fluoride. So, such as tin, and we know that the 2 over here means positive 2. So we know tin has a positive 2 charge, and using the periodic table, counting from fluoride to the group 18, or the stable noble gases, we find that fluorine, or fluoride, which we'll be using in this case, as stated by the equation, has a -1 charge. We will be using the elemental symbols Sn and F, which also appear on the periodic table as the symbols for tin and fluorine, or fluoride in this case because it's written in the formula. So there's a method called switch, drop, and reduce. So we start with the tin and the fluoride, and we take their charges and add them as the superscripts up here at the top. So these are the original equations. Then we do the switch method, where we switch the charges. So the -1 went to tin, and the positive 2 went to fluorine. And then we drop. We dropped the charges both down to become subscripts. So Sn actually has a 1 subscript, but we usually don't include these when they have a 1 subscript. It is just expected that you know that they have a 1 subscript without writing it in. So it would be SnF2, which is basically the same thing as tin 2 fluoride. There's this other method called reduce. If you look at the note down here, we begin to see that in the drop section, as I noted before, both the numbers and charges literally drop. They drop down, and the charges go away because we do not write the charges as the subscripts. Going back to the reduce method, we notice here that there was nothing to reduce because it is already in a 1:2 ratio, and thus it remains the same. Otherwise, if we had a 2:2 ratio, that would reduce to 1:1. More compounds, which include transition metals. So, CuI, we will be naming this one. So we know Cu stands for copper, and I stands for iodide. If we note on the periodic table, the I is in group 17. In group 17, in order to achieve a noble gas-like state in group 18, I would have to gain a -1 charge, or an extra electron. I would have a -1 charge. And since the subscripts are reduced as a 1:1 ratio here, we know that Cu will have a +1 charge in order to cancel out with the -1 charge and give us CuI. So we know that it will be copper 1 iodide. Note that we only include the charges for the transition metals. We do not need to write the charges in parentheses for the metals on the left side of the periodic table, nor the nonmetals on the right side. So we move on to chromium 2 sulfide. as we see here the name. So we got this by doing the inverse of the switch drop reduce method. So when we do that, we go CR and S. So now we have the 2 and the 3. So since we know that the items were switched, that means we had the -2 over here and the +3 over here. And then going backwards, we realize that CR has a +3 and the S has a -2 charge. So since we know that this is a +3, this corresponds to the Roman numeral 3 in the parentheses after chromium. And then sulfide remains without writing anything in the parentheses, because as we said before, nonmetals do not get to have the parentheses written down, because it is expected that we can count from sulfide that we need 2 electrons in order to achieve a noble gas-like or stable state. The last one is copper 2 sulfide. So we will be writing this equation. As you see, I already have the answer on this side right here, copper 2 sulfide. So let's start. So we know copper, Cu, has a +2 charge, given the Roman numerals. Then we move on to sulfide, and as we see from the periodic table, sulfide needs 2 electrons in order to achieve a stable state. So that means it would need to gain -2 charge, or 2 electrons, since electrons have negative charges. When we switch these charges, we go Cu -2, S +2. Switch, and then drop, so we get Cu2, S2, and then at the end we get reduced. This is one of those cases where we do reduce these, and it turns into a 1-to-1 ratio since these 2's cancel out. Polyatomic ions. It's good to have a basic knowledge in memorizing some of the polyatomic ions. They may differ between classes. I will not go over the polyatomic ions in this section, so it is just a general note that they come in handy when dealing with chemical concepts or writing equations and formulas. So it's a good idea to have some of these memorized, especially the common ones. Some binary compounds use prefixes, which include sometimes non-metal to non-metal bonding, and those are usually called covalent compounds. These are to distinguish the ratio of atoms. So one example is carbon dioxide. As you see here, we have the prefix here di, meaning 2. So CO2. No, we don't need to call carbon monocarbon. We don't need to do that, because it is already implied that for every 2 oxygens there is 1 carbon. So for every 2 oxygens, only 1 carbon is needed, and that is already implied by stating carbon dioxide, and so stating monocarbon dioxide is an incorrect form. I did include the prefixes down here. As we see here, mono means 1, so 1 atom, and sometimes we use the prefix mon, such as monoxide, if you ever heard of monoxide, such as carbon monoxide. We don't call it monooxide, we remove the extra vowel and just call it monoxide. And then we go down in a simple chart. So we have di, which is 2, tri, which is 3, tetra, which is 4, penta, which is 5, hexa, which is 6, hepta, which is 7, octa, which is 8, nona, which is 9, and deca, which is 10. Some easier ways to remember this, such as tri is almost like a triangle, 3 sides. And same thing with other ones. You can call these polygons, such as penta. We can remember a pentagon, which has 5 sides, or hexa, which is a hexagon, or hepta with a hectagon, or octa with an octagon, and you understand the point with these. So these aren't really hard to remember. They just need some tricks to get around it. Or you can just memorize mono is 1, di is 2, tri is 3. There's nothing wrong with that either. So once again, these come in handy for naming binary compounds, usually for covalent compounds, for non-metal to non-metal bonding, such as carbon dioxide, carbon monoxide, or even other compounds such as sulfur dioxide. And note, I am saying a lot of dioxides, but there are other compounds out there that you can use it with. Thank you for watching this video. I hope you learned some new things today.